Okay, this is the lecture for MSc 5532, Lab 2, Energy to Go, Fabrication, Testing, and Failure Analysis of Lithium-ion Batteries. I should note that these lecture notes, as well as the lab procedures, tutorial videos, and pre-lab quiz will be available on Carmen. Okay, so for this course, for this lab module, some helpful resources include your 2241 Structure and Characterization textbook, as well as textbooks from Thermodynamics of Materials, Structure and Characterization Lab, so 2251, 2331, as well as some crystallographic references from MSc 2010 Introduction to Engineering of Materials textbook. The goals and objectives for this lab module are as follows. For the goals, successful students will be able to understand the mechanism of charge storage for lithium-ion batteries, and that you'll be able to assemble, electrochemically test, and comprehend reported data for a lithium-ion cell. For the learning objectives, at the end of the lab module, you'll be able to describe components of an electrochemical cell, describe the mechanism of charge storage in lithium-ion batteries, fabricate and assemble an electrochemical cell, collect galvanostatic cycling data, analyze the properties of these active materials, propose some failure mechanisms in the electrochemical cell, and also identify changes in structure in electrochemically active materials. The rest of the lecture will be outlined as follows. So we'll start off with definitions that you'll need to know, give some historical context for the evolution of batteries. We'll discuss also figures of merit, description of electrochemical cell. We'll discuss how thermodynamics and crystallography predict the electrochemical performance of a cell based on the materials that you choose. Talk about the assembly of the cell, cycling of the cell, and other parameters that affect how an electrochemical cell behaves, such as the cycling rate, and then other mechanisms of failure. So let's start off with definitions. What exactly is a battery? Well, a battery is an electrochemical storage device that converts chemical energy to electrical energy. So what are some metrics by which we can talk about or describe a battery? Well, voltage and capacity are two metrics by which we can describe the characteristics of a battery. And for this course, we're considering secondary cells or rechargeable cells. There are, of course, other types of cells, such as primary cells, where you can use it once, but they cannot be recharged. So the voltage is the electric potential energy of the cell. And we'll talk about how the thermodynamics of the materials that you pick determine the voltage. The capacity is the stored electric charge in the electrochemical cell, and that can be computed as follows. Here we have Q representing capacity, and that's current, the applied current times time. In this case, it's in hours, and that gives us amp hours. The capacity and energy is amp hours, which is also the discharge current of a battery that can be provided over a certain amount of time. The energy that's in a battery is the voltage times the capacity. So in units here, you see voltage times amp hours, which gives us watt hours. And that's how we typically express energy. Specific energy, we normalize it gravimetrically, so watt hours per kilograms, or volumetrically, watt hours per liter. And by which mass are we talking about? Which kilogram? So typically we talk about the active material, how much active material you have in your electrochemical cell, and the volume of that material. So these two parameters, energy and power, are quite useful because it will let us know the loading capability of a battery for a number of uses. You're going to want to know the energy that's available or the power that's available at a certain voltage over time. An analogy of energy and power can be described in this figure here, where let's say you have water that's contained, some volume or some mass of water that's contained in this Nalgene bottle here. The specific energy, how much water is in the bottle is a specific energy, and how much of the flow of water that's being poured out of the bottle, well, that's governed by the specific power of the battery. All right, historical context. Battery technology has come a long way. Many advancements in various types of energy storage technology that you see here on this plot has been towards increasing specific energy and specific power. We'll be focusing on lithium-ion battery technology for this lab course, so some of those materials that you see are in blue here. However, there are many types of energy storage technologies, such as lead-acid battery that you may be familiar with, nickel-cadmium, and also nickel metal hydride, just to name a few. So the leaps in lithium-ion battery technology advancement have been made by many scientists over the years, and there's still a lot of work to be done. Recently, the Nobel Prize in Chemistry was awarded equally to 3 scientists in 2019, and they are John Goodenough, Stanley Whittingham, and Akira Yoshino for the development of lithium-ion batteries. Specifically, their contributions are as follows. So you may be aware of John Goodenough's major contribution in the 1980s studying ion conduction. In fact, he developed the lithium cobalt oxide technology, in which cobalt oxide is the cathode material, and that's used worldwide commercially. And that technology was commercialized more so by Sony in the 1990s. Stanley Whittingham in the 1970s developed also innovative cathode type materials for lithium-ion batteries. Here he looked at titanium disulfide for hosting lithium ions in an electrochemical cell. However, lithium cobalt oxide does have higher voltage than titanium disulfide. Akira Yoshino made major contributions by incorporating carbon instead of lithium metal as the anode. And this has improved safety in lithium-ion battery technology immensely. And we'll talk about why that is in terms of preventing lithium dendrite formation, which is deleterious for batteries. Okay, number 3. Figures of merit. You can see here in primary batteries, when we talk about figures of merit, we're talking about how much energy does a battery have, what operating voltage does it work at, and what kind of shelf life does it have. So here you see for primary or non-rechargeable battery technology, alkaline metal batteries have about 200 watt-hour per kilogram, lower operating voltage of 1.5 volts, and about 10 years shelf life. You could see here, as you change materials to, let's say, lithium iron disulfide, lithium manganese oxide, and so on and so forth, you could see that the energy does increase slightly or dramatically, more than 2x, and also the operating voltage is higher, which makes it useful for a wider number of applications. For secondary or rechargeable type batteries, you can see that there's been huge improvement in increasing the energy density here, going from 30 watt hours per kilogram in lead acid battery all the way to 2,500 watt hours per kilogram when you change the cathode to sulfur, and the anode is lithium. But that's actually a different type of energy storage technology than what we'll be talking about. We'll be focusing on intercalation base type materials where we insert lithium ions and de-insert them and not just convert the cathode material. You can see here that the voltage is quite high, 3.5 volts versus lithium. In that the cycle life, you can cycle about 800 times before dramatic capacity fade occurs. So it's been quite an improvement. And as the energy density, gravimetric energy density here, increases, what we're looking at is batteries that have less weight and that are smaller, which of course is attractive from a financial and manufacturing point of view. So concomitant with the increasing energy density that you just saw, the cost of lithium batteries have also dramatically decreased over the last 10 years. This makes lithium-ion batteries more amenable for electrification of vehicles, and that's evident in these two plots here. So the plot on the left that you see here, you can see that the lithium-ion battery sales have increased over the year, and particularly so for automotive industry worldwide. For the plot on the left, you see that, for the plot on the right, you see that the costs per kilowatt hour has also decreased since 2010 by about 33 to a third of the price, which makes it quite amenable to the electrification of vehicles. And as you already know, the incorporation into electric batteries into electric vehicles has already been happening for quite a while now. And here are some performance metrics. What we are really aiming for, on the extremely efficient end, is that the cost is less than $100 per kilowatt hour for a car that you can drive 300 miles, greater than 300 miles, and that the charge time is less than 15 minutes. And of course, we also want to lightweight the material. And here you could see for the various manufacturers, Tesla, BMW, Nissan, Volkswagen, Chevrolet, Fiat, Kia, so on and so forth, in the models of the different cars, you could see the battery sizes as well as the types of chemistry. So these initials, keep that in the back of your head. For now, we'll talk about, what these initials actually mean when we talk about the crystal chemistry of these materials, but you could also see here that they're defined below. So NCA has nickel, cobalt, aluminum in them. NMC has nickel, manganese, cobalt. LMO has lithium, manganese, oxygen. C is for graphite, so that's the anode, and LTO is also the anode, so it's a different type of anode, and the battery supplier. So you could see, based on the different chemistries, you can really achieve different vehicle ranges here on the high end. That uses a combination, some solid solution of nickel, cobalt, aluminum, as you see here. Okay. So there's quite a variety of range of vehicle distances that you can go based on the various types of chemistries, the different types of materials that you pick. So let's go through some calculations. Here, let's say you have a commercial battery that's rated at 3.5 volts and 85 milliamp hour. What are you supposed to do with this? Well, first you can calculate the energy of the battery. We mentioned that 1 watt hour is a volt times 1 amp hour. So here we have the volt and amp hour, but in milliamp hour. And so we can calculate the energy by multiplying the volts by the capacity here. So that's 3.5 volts times 85 milliamp hour. We convert milliamp hour to amps. Sorry, milliamps to amp. And we get 0.3 watt hours, which is equivalent to 3 times 10 to the negative 4 kilowatt hours. Now, that might not mean much, so let's have a point of comparison. How much energy is in a gallon of gasoline? So that's about 35 kilowatt hours. If we assume that the car operates at 20% efficiency usage of that gasoline, we could ask ourselves, well, how many batteries would we need to have to be equivalent to have the same equivalent energy as 1 gallon of gasoline? Well, we calculated before that each cell has 3 times 10 to the negative 4 kilowatt hours, and 20% of 35 kilowatt hours is 7 kilowatt hours. So we would need about 20,000 cells, which is quite a lot, but that is actually, thousands of cells go into a battery pack for when you buy, let's say, electric vehicle. Here just is a commercial example in which here you see a battery pack rated at 24 volts, 250 amp hour, or 5.3 kilowatt hour in energy. And here it says there's 444 Panasonic batteries. So clearly the voltage and capacity for each battery, for each electrochemical cell within this battery pack is a little bit different. And so we can just do a math check. So 24 volts times 250 amp hour, that's about 6 kilowatt hours of energy there. And it's rated at 5.3. So there's some loss in, thermal management in the battery pack and other engineering aspects. Okay. So in terms of description of a battery, another way that we describe another parameter is the C rate. And that describes our discharge rate, and as well as our charge rate if it's a symmetric charging and discharging. So here's an example. The way we talk about it is we talk about a C over N number. So C over something, in which N is the number of hours required to discharge the capacity. So in this case, lithiate. So 1C is described as, to fully discharge within 1 hour. 2C is to discharge within half an hour. That's extremely fast. C over 2 means in order for you to discharge, or let's say lithiate or charge or delithiate fully in 2 hours. C over 10 is that it's going to take you 10 hours to discharge or lithiate. And of course, the amount of capacity and energy that you can achieve does depend on which C rate you're operating at. And we'll go into detail in a little bit as to how this is the case. So section 4 will be on the description of the electrochemical cell. So here in a typical electrochemical cell, we have a cathode, which is the positive electrode, the anode, which is the negative electrode. Here you also see represented by this gray rectangle, the separator. Okay. So upon discharge, you can see here the green lithium ions are transported from the anode side to the cathode side. And this graphic is to represent lithium cobalt oxide as an example of a cathode material. And the gray material here, that's graphite. That could also just be lithium, so you could just have a sink of lithium at the anode side. And then upon charge, the opposite happens. Lithium ions are transported from the cathode to the anode. And the electron current, as you can see here, goes in the same direction. So upon discharge, anode releases electrons to the negative terminal and the ions into the electrolyte. And the cathode accepts the electrons. And upon charge, the reverse of the discharge process happens, where lithium ions are deintercalated from the cathode and the current is in the opposite direction. Look what's happening at the electrode-electrolyte interface. Well, electronic current is changing from ionic current. In terms of what's happening chemically, let's talk about the reduction-oxidation reaction. So upon discharge at the cathode, here I just have generically lithium MO2, where M is let's say a 3D transition metal. So in that case, let's give the example of lithium cobalt oxide. Well, lithium cobalt oxide upon discharge, as you're delithiating, upon charge, so the right arrow here, as you're charging, you're delithiating. So you start from 1 molar equivalent of lithium and you're removing some fraction of that. So it's 1 minus X. And to balance the reaction, on the right side, you also see lithium ions and, of course, X molar equivalents of electrons to achieve charge balance. Upon discharge, you're lithiating the cathode, and thus the arrow is in the opposite direction. At the anode, if we have graphite, or so that would be C6, or maybe even something as exotic as fullerenes, so that'd be C60, but you have some carbon material, and upon charge, that becomes lithiated. As you see here, upon discharge, the lithium ions are removed. So then if you add the two half reactions, you get an overall reaction of LiMO2 plus carbon going to Li 1 minus X, MO2 plus LiXCN. So that's upon charge, and then the reverse reaction happens upon discharge. So here we see the half reactions again at the cathode and anode. And let's talk about the voltage. So for the cathode, at the cathode, for this half reaction to happen, that's rated at 3.7 volts versus lithium plus. At the anode, if you have a carbon material, let's say graphite, that's 0.2 volts versus lithium plus, in which this half reaction, lithium being ionized to lithium plus and electron minus, that's set at negative 3.01 volts versus standard hydrogen electrode. And so here, how we figure out the voltage of the cell is that we look at the voltage, or E is the voltage of the cell, is the cathode minus that of the anode. And so here we can see, well, the cathode is at 3.7 volts. It's versus lithium, but lithium is 3.01 volts offset from SHE, or standard hydrogen potential. And the anode is 0.2 volts versus lithium, which is once again offset by 3.01 volts versus standard hydrogen potential. And so what we get overall is 3.5 volts. Now, if this cell were just versus lithium and not versus carbon, then we will have a 3.7 volt cell because it's no longer offset by 0.2. So now let's talk about the thermodynamics of the cell. In terms of phase transformation and thermodynamics, let's review. So the energy of reaction, let's say A plus B going to some phase AB, what we see here for the Gibbs free energy as a function of composition plot, we can see that there could be phases, composition in which has a higher Gibbs free energy than, let's say, something that's for composition that's in the middle. When we talk about the open circuit potential, we are measuring the Gibbs free energy of the system as there is no current flowing. And so the only, the chemical driving force on the ionic species in the electrolyte is just balanced by the electrostatic driving force. And the materials in these batteries experience diffusional and structural phase transformation during the operations of these batteries. And as you're applying current to drive ions from one side, cathode to anode, anode to cathode, what's happening is that you're operating under non-equilibrium conditions. So when we measure the voltage of the cell, it's telling us, it's giving us a snapshot of what the Gibbs free energy looks like in the cell. Okay. So typically what you would see from, let's say, measuring the voltage as a function of time, if we're applying current, then we're measuring, the amount of lithium ions that are being transported over time. And we may see a voltage drop, as you can see here from this commercial cell. You can also see that the cell behaves differently, right? The thermodynamics of it behaves differently at different temperatures. So how do we tie thermodynamics to when we just measure the voltage of the system? Well, as you can see here, the chemical potential is the Gibbs free energy, the change in Gibbs free energy divided by the change in the composition, where X here is the lithium concentration. So let's say you have first, no lithium, where is here on the right of the phase diagram, of this plot, you have a fully lithiated system. So you can see that you can have 3 different types of cases to start off with, where you could have a voltage as a function of lithium concentration looking like this, where it's a little bit slopey, or you could have dramatic decrease in voltage and then a plateau, and then dramatic decrease in voltage again. Or you can have rapid change in voltage, plateau, and then a jump, and then another plateau, and then change in decrease in voltage again. Well, when you measure the voltage, what you're really measuring is a change in Gibbs free energy. And so here's the corresponding change in Gibbs free energy, where here you take the slope, dg dx, they'll give you the chemical potential, and the difference between the cathode versus your anode. So if your anode is lithium, then that would just be 0 divided by E to convert to voltage. And so integrating voltage will give you the Gibbs free energy. So let's look more closely at each one of these scenarios. So here you can see, let's talk more concretely about a system with lithium cobalt oxide. Let's say there's some electrolyte, so that's some salt in solvent, and then in the separator, and then an anode. So let's say it's lithium anode. So what you see here is that when you measure the voltage, it tells you at when there isn't lithium here, that it's at a higher voltage and thus at a higher Gibbs free energy. And as you lithiate the system, here's a discharge curve, and you're increasing the concentration of lithium in your compound, your chemical potential is changing, as you can see here. The chemical potential is changing because the Gibbs free energy is changing, and the chemical potential is just the derivative of Gibbs free energy as a function of lithium concentration. And so far I've said that the chemical potential of lithium is treated as a constant because we're using lithium metal. Let's say you have a voltage profile that has a plateau in it. Same equations apply. So if there's a plateau, you could see that here, between X1 and X2 compositions, you can relate that to the number of phases that are present. So you can see here, there's a common tangent line, and MA is the unlithiated, LI-MA is fully lithiated. So in between these two compositions, there's a 2-phase coexistence in the common tangent region, as you can see here, between phase alpha and beta. if there is a jump in the voltage curve like that you see here, right between composition X2 and X3, what that's saying is that this dip is saying that there's actually a third phase that is a stable intermediate between alpha and beta. Okay. So here we see, some realistic discharge curves. So here you see on the y-axis cell voltage as a function of the percentage of the capacity that's discharged. And so we see here for different types of batteries that you can have, this slopey type of voltage changing over time. You could see some resemblance of a plateau here as well. Sometimes there's a combination of both plateau as well as change in voltage, right? So not just for lithium-ion batteries, but also for lead acid and other types of alkaline type materials. So even without discharging, you can also have, let's say, you can measure just open circuit potential. If the composition is different for your material, so it's not exactly lithium cobalt oxide, Li1CO1O2, but you have, let's say, different compositions of lithium, Lix, COO2, you could see that the open circuit potential, so the difference between the chemical potential difference between cathode and anode, will give you different values in the voltage, right? Because it's a difference that gives free energy, and here it's divided by the number of electrons times 10 Faraday's constant. Here you see some typical voltage curves, and here it's volt versus capacity. You'll also see sometimes voltage as a function of capacity and equivalent moles of lithium. So the lithium ion concentration is listed here, and that's equivalent to the amount of capacity down here. So you could see that if you increase the amount of lithium ion deintercalation, so you follow this curve here, you could see that at some point, there's a dramatic change in the voltage here. And then if you keep on going below 3.6 volts, you could see that there's quite a bit of change, very dramatic drop there. Okay, so how does the crystallography affect the thermodynamics and then eventually the electrochemical performance that you observe? Well, whenever you take materials, it's always a balance of sustainability, costs, and performance, right? So here we see three types of materials. So we see here a layer type material, a spinel type material, and an olivine type material. And within these three types of materials, you see I've listed some examples of substitutions or different solid solutions that are formed by taking out some of the cobalt and introducing some nickel or manganese. So you'd see here that from lithium cobalt oxide, if you introduce nickel and aluminum, people often call that NCA, or if you substitute with nickel or manganese to reduce the cost because cobalt can be quite expensive, that's typically called NMC or NCM. And the ratios of X to Y to Z, you could see here that there's been quite a bit of development to increase the amount of nickel and decrease the amount of cobalt to not only decrease cost, but also increase voltage. We won't be focusing on anode materials in this lab module, but just to note, instead of the lithium metal that we'll be using commercially, people have used graphite, lithium titanate, and also silicon. And these types of materials are used for a number of reasons, for either increased safety or increased capacity, as you can see here. And some of these types of materials, like silicon, is used to alloy with lithium on the anode side, and other materials that have been explored, as you can see here, are antimony, germanium, and silicon oxide, so expressed as SiOx. So why change this transition metal, right? So you can see here that the potential of the cell, the voltage of the cell increases with increasing number of electrons in the d orbitals of the transition metal ions. So here you see in this plot that as you increase the number of electrons in the d orbital, that the voltage increases. Okay? So here, let's take the example of lithium cobalt oxide. So zero valent cobalt or metallic cobalt is 4s to 3d7. And in lithium cobalt oxide, cobalt is 3+. And so in fully delithiated system, you have just cobalt oxide or COO2, and that makes cobalt a 4+ cation. And so that's 4s, 4s0, 3d5 in the oxidized state. So you can see that substituting with nickel does increase the voltage, but there are some instabilities when you cycle these types of cells. Manganese is also cheaper, but the voltage decreases a little bit. In terms of abundance of materials, one of the reasons why people are looking to substitute cobalt with other transition metals is because there are certain geopolitical issues associated with mining cobalt and where these mines are located. And you can see here the cost of cobalt. Here, the 5-year price range in US dollars per pound for cobalt is higher than that. So it's higher than that of, let's say, manganese, right? And also some nickel. So indeed, increasing nickel and lithium content can increase performance, but it could lead to thermal instability. You could also see here that lithium is quite costly relative to, let's say, something that's more abundant, like sodium, but that's another discussion beyond the scope of this course. And you can see here that we're not really focusing on conversion based anode materials, as we'll be focusing on cathode materials, but I should mention that silicon has been looked at and commercialized for increasing capacity, but one of the things that we have to consider, of course, is unlike graphite, using silicon, you form, there's irreversible volume expansion and contraction, and so so nanostructuring is one of the ways to go, but there's a lot to do there for improving that type of technology. So here's a review of Bravais lattices. So you remember from one of the earlier classes that you've taken in your MSc career, that we have 14 Bravais lattices, and they can be made up from 7 crystal classes that you see here. So you can see increasing symmetry here. So the systems that we'll be looking at have either orthorhombic symmetry, cubic symmetry, as well as trigonal symmetry. So let's start off with our bar 3M, lithium cobalt oxide. You can see here that this is the unit cell for lithium cobalt oxide. Look at the last parameters. A and B are the same at 2.816 angstrom. C is much longer at 14.054 angstrom. And these last parameters were obtained from this paper that you see here down below. The lithium sites are at 0, 0, half, cobalt is at 0, 0, 0, and oxygen is placed at 0, 0.26. So let's take a look at where those atoms are. So I'm going to change over to Vesta. So you can see here, let me change back to the boundaries so that we're just looking at 1 unit cell. So you can see here that cobalt is at 0.000, oxygen is at 0.26, and lithium is at 0.0 half. Okay. So you can see where that is in the unit cell. And now we'll change the boundary and increase it to, let's say, 3 unit cells in X, 3 unit cells in Y. And also let's look at polyhedra view. So we see here that within each layer, there is COO6 octahedra, so that you could see here in the blue. So there are 8 faces, and they are edge sharing. And in the van der Waals layers here, you can see the lithium ions in the crystal structure. Okay, so here you see another view of the unit cell, and then the view with the unit cell propagated. So when you start off with lithium cobalt oxide, that's Li1, COO2. When you charge, you de-intercalate or remove lithium or delithiate, you could see here, and it's voltage versus composition plot. And then you can also discharge or intercalate lithium ions back into the system. So here, what you could see is that there's actually a little bit of a loss. And this change in composition is indicative of the fact that as you de-intercalate down to from 1 to 0.4, so there's a 60% change, you could see that upon lithiation or intercalation, that it's not fully back to the original composition, but very close, right? So it's 0.9 something, 0.93. It is a very slow rate. If you see a report like this, the rate, it's saying that the time it takes to charge, de-intercalate lithium ions, and change the composition by 1 is actually 50 hours, right? So this is about 60% of that 50 hours done at near room temperature. And the X-ray diffraction of lithium cobalt oxide, as you can see here, ranging from 10 to 50 for 2 theta, using a lab X-ray source, lambda 1.54 angstrom. This is what it looks like for the R-bar3M structure. So let's look at this peak right here. So what happens to the structure when you intercalate and de-intercalate, or de-intercalate, intercalate, charge, discharge? So here's the same plot again. We could see that going from 1 to 0.5, that there's a 1.4% increase in the C lattice parameter. And what others have done is that they've actually performed what's called in situ X-ray diffraction. And X-ray diffraction is shortened to XRD. So in situ XRD means that they have fabricated a cell and looked at the X-ray diffraction through a window as the battery cycling. So at no point did they have to take apart the cell to look at the structure. So cycling is done on the cell as you're collecting X-ray diffraction. And that was done by Reimers and Jeff Don, who's made major contributions in the battery world. So as you can see that as X decreases, the peak shifts from higher 2 theta angle to lower 2 theta, lower angle. And that's indicative of a lattice parameter increase. At 3.93 volts here, if you look at the 003 reflection of lithium cobalt oxide, you see that there's indeed a there's a new reflection that forms. So not only is it decreasing now, there's a new reflection that forms here. So it's shifting to lower 2 theta, and then there's a new peak that emerges here. And so this new reflection is indicative of first order phase transformation. And in fact, it's a transformation to a monoclinic phase from a trigonal phase. Another type of material that you'll be working on in the lab module is lithium manganese oxide. It's a spinel type structure, as you can see here, and it's evidently quite different than what we just talked about in the layered lithium cobalt oxide structure. It's cubic, so all the angles of the unit cell are 90 degrees, and the lattice parameters are all the same, so A equals B equals C at 8.251 angstrom. The lithium manganese ion and oxygen ions are located at these fractional coordinates within the unit cell. And so you could see that this is a different type of crystal structure. It's not layered, but in fact, it's a 3D type material in which the lithium ions go in and out of these channels that you see here. Okay. And you could see that the lithium ions are in tetrahedral locations, whereas the manganese are in octahedral cages, as you see here. Okay. So here's another view where the lithium ions will come in and out of the page as deintercalation and intercalation happens. Here's an X-ray diffraction pattern, and you could see that as lithium content changes from 1 all the way down to 0, that the lattice parameter is actually increasing. Now let's look at the voltage as a function of composition. So for lithium manganese oxide, Mn2O4, you could see here that upon charge, that's delithiation. Upon discharge, that's lithiation. You could see that the performance is different at different temperatures. And something to note also is that the decomposition of this material to different polymorphs of manganese oxide also, limits its ability and usage at higher temperatures. One thing to note here is that the charging, you could see it sometimes overcharging. So the charge is more than the discharge. That's usually an indication of electrolyte decomposition. So the salt in your solvent, and possibly the solvent as well, is reacting with either the anode or the cathode or both, and that is changing the interface that's at the electrode-electrolyte interface. Okay, and we'll talk more about that in a little bit. So what's happening to this crystal structure upon delithiation? Okay, so for LiX Mn2O4, you could see here, this is a voltage curve. So the voltage is increasing upon charge. It's a function of time. So what's happening here? Well, we track from 1 to 55. So 1 to 55 here. We can see that indeed there is an increase of the 511 peak, increasing to higher 2 theta. Okay, and this is at room temperature. All right. So for the third type of material, you see here lithium iron phosphate. So it's a polyanionic material, and you can see that's orthorhombic. So all the angles of the unit cell are 90 degrees. The lattice parameters are all different. A is 4.787 angstrom. B is 10.086 angstrom. C is 5.939 angstrom. And the ions are listed at these fractional coordinates within the unit cell. And what you see here is, once again, different than that of the 2 previous crystal structures that we talked about. You can see here the lithium ions in black are coming in and out of the page. And in the second rendering, from a different angle, you could see that the lithium ions are also coming in and out. And so let's switch over to Vesta to see what that looks like. So let's look at lithium iron phosphate. You can see here from one perspective, going down the z-axis, that lithium ions are coming in and out of the page. So you can see here, these are the tunnels of which lithium ions will be coming in and out. Okay. Okay. So what we haven't talked about so far is how particle size and processing conditions affect performance, right? We talked about the thermodynamics, we talked about phase transformation, but how we process a material and the before we even cycle the material will affect the performance or the capacity achieved. And so here you could see for lithium iron phosphate that smaller particles with greater surface area can reduce inactive particle, can reduce the amount of inactive particle centers that you have. So here, the lithium iron phosphate that's been processed, synthesized, and sintered at 800 degrees C versus lower temperatures at 675 degrees Celsius, you could see that the capacity that's achieved is much higher than that of the sintered and the particles at 800 C. So the particles here are larger and the surface area is smaller than those particles that are at 675 C. And so you can see that for the larger particles, there are inactive inactive parts of the lithium iron phosphate, which of course can can decrease the capacity that's achieved here. When we increase cycling rate, so let's come back to C rate, when we increase the C rate, we also can decrease the capacity that is achieved. So here for lithium iron phosphate, we could see that cycling very slowly, so discharging and charge, so discharging at C over 10, so that's over 10 hours, you can achieve higher capacity, 150 milliamp hour per gram, versus cycling at an extremely high rate of 5C. This is extremely high. And you can see that the capacity that one can achieve is lower, and thus the energy density is lower. But what Linda Dazar's group has shown back in 2001 is that you can coat lithium iron phosphate with carbon grown in two different ways, and you can achieve high capacity, high capacity, close to theoretical capacity, and at room temperature, right? So you can see here that this is quite high, and that can be maintained over 800 cycles. You can also increase the electronic conductivity of these electrode materials by incorporating substitutions with cations such as manganese, aluminum, titanium, zirconium, niobium, and tungsten that you can see here. And you could, and that was demonstrated by Yet-Min Chang, MIT, and so you could see, but also it suffers from the same fate where if you charge and discharge at faster rates, as you can see here, from C over 10 all the way to very high 21.5 C, that the capacity does decrease, as you can see here. So how does the structure of lithium iron phosphate change? Well, here, as reported by in situ X-ray diffraction pattern by Shin and coworkers, that as you deintercalate lithium, so from 0.1 all the way to 41, you could see that there is a phase transformation from lithium iron phosphate or triphlite. You can see the 200 peak here, transforming to the heterosite or this iron phosphate structure. This is the 200 peak of that compound. So if we rotate this curve 90 degrees, we can align it with the X-ray diffraction to see that Upon charging, that you could see the emergence of the heterocyte peak here early on, as you can see, and then it transforms to a 200 heterocyte. Upon discharge from 0.1 to 0.41, as you can see here, that there's actually asymmetry at the rate of phase transformation. So here you see the peak shifting this way, and then upon discharge, coming back from heterocyte to triphlite, that is actually not the same. So there's been quite a number of studies done to look at the lithiated region here, the intermediate composition or intermediate capacities here, to see what is happening. And recently in 2014, it's been demonstrated there's actually a metastable solid solution phase in between here at high cycling rates. Okay, so there's still a lot of work to be done to understand the phase transformations in all of these battery materials. All right, so part 7, assembling a cell. Well, for autumn 2020, you will not be casting an electrode from the slurry, but we will go over it in just briefly so that you have an idea of what goes on into preparing an electrode that you'll be working with before you assemble. So here you can see that first you can weigh out the powders, mix it either by hand, mortar and pestle, and you combine active material with some conductive carbon and polymeric binder. And then you could also mix it with a high-speed mixer that you could see here before assembling. And the assembly is done in argon glove box that you can see here. So this is the type of glove box that you'll be working with for the in-person lab. And you could see that they, whether you're making a coin cell that you typically see or what's called a split cell, that the assembly will be the same in terms of the ordering. And we'll go over that when you're in person. So here I have a video that's from the Clean Energy Institute, courtesy of Jared Olson from the University of Washington, in which we'll go over very briefly how the materials are combined. So I'll annotate. So at first, let's go to, before you get to this electrode material, that electrode that you see here, that you first have to combine the powder. So here, Jared Olson is going through, the different types of materials that he'll be combining. In his case, it's actually anode type material, so silicon. We'll be working with cathode type material, but the process will be the same. Percentages are different, but the process won't change. So here, the scientist is putting in a few milliliters of N-methylpyrrolidone, which is the solvent that's used to mix all the powders together, as you can see here. So that's being mixed around. As the powders are mixed, you could see that a paste is forming, and it will become a slurry. You can see there. And once that is well mixed, then that will be doctor bladed onto a piece of copper current collector. We'll be using aluminum for the cathode side. So here he's putting down the the copper current collector, and then the paste, the slurry that was just mixed recently. Okay. And then a doctor blade is used to uniformly spread the slurry. Okay. And since it's done by hand, It's not over a very large area, but it will make several electrodes, once punched out. So you can see there. And then the electrode is left onto the hot plate to dry, and you can see as N-methylpyrrolidone, or NMP, is dried. You could see here that there's a change in color. And you can see that it's all done in a fume hood, so the scientist is not breathing in NMP. And then there are a number of ways to punch out an electrode, either with a punch where you can just pull it down, or here with just a hand punch that you can just hammer out. So nothing too fancy. And there you have it, an electrode that's ready to go for assembly. Okay. And you can watch the full version here on YouTube. Okay. We will also have a tutorial video for you on how to actually do the assembly once you have the electrode. And so the link to that video will be provided on Carmen, and you'll get a notification about that as well. Okay. Okay, so section 8, cycling the cell. Before you cycle a cell, and I will be there in the lab to supervise, of course, but there's some safety considerations to take into account so that we don't have dangerous operating conditions. Right? First, we need to talk about, and this is discussed in your lab procedure, the optimal voltage windows. You do not want to go outside these windows because generally, one, it just doesn't result in optimal charging and discharging, but also it can cause other issues such as oxygen evolution going beyond 4.3 volts versus lithium for lithium cobalt oxide. And of course, oxygen evolution is a concern for outgassing. Right? Increased pressure of flammable gases is of course a real safety hazard. Okay. Let's look at how to calculate the theoretical capacity of lithium cobalt oxide. Here the capacity is Q in milliamp hours per gram. N is the number on the charge carrier. In this case, it's 1. F is Faraday's constant, which is 96,485 coulombs per mole, converted to amp hour is 3,600 coulombs per amp hour, divided by the molecular weight of lithium cobalt oxide, which is 97.87 grams per mole. And how we calculate the molar mass is that lithium is 6.94 grams per mole, cobalt is 58.93 grams per mole, oxygen is 16 grams per mole. But according to the stoichiometry, there's two oxygens, which comes out to 97.87 grams per mole. And when we do this calculation, convert from amp hours to milliamp hours, we get a theoretical capacity of 273.84 milliamp hours per gram. Let's say, practically, we only want to transport half of the theoretical capacity. So that would be then, in example 2, that will get us a capacity of 136.92 milliamp hours per gram. Okay, so now let's talk about calculating capacity in your cathode. Here we have the theoretical capacity of lithium cobalt oxide, once again, of 273.84 milliamp hours per gram. And now we want to determine the active mass in the material and how much applied current we should apply to discharge charge over a certain number of hours. So as you've seen with the slurry casting, that the electrode isn't 100% of the 100 weight percent of the material, of the active material. Let's say the weight percent is 90 weight percent lithium cobalt oxide, 5 weight percent of the conductive carbon, 5 weight percent of polymeric binder. Well, let's say the electrode, the composite electrode weighs out at 3 milligrams for the active for the composite, which of course does not include the current collector. So 90% of that is 2.7 milligrams. So 2.7 milligrams of the composite is lithium coal oxide. Well, the capacity that you can achieve with that mass loading is 0.74 milliamp hour. So then we can determine the amount of applied current that's needed to discharge within X hours by dividing the capacity by the number of hours. And so for a C over 10 rate, we would take the capacity, 0.74 milliamp hours, divided by 10 hours, and the applied current would be 7.4 times 10 to negative 2 milliamp, or 7.4 times 10 to negative 5 amps. And then the potential stats that you'll be using, they'll by default be in amps. So be sure that you check your units. Another metric by which we discuss cycling on a cell is the Coulombic efficiency. And that is the discharge capacity divided by the charge capacity that's achieved times 100%. So those are the two values that you see here. So when you have a charge capacity that is greater than that of your discharge capacity, that can be attributed to electrolyte decomposition, overcharging because of that reason, or a number of other phase transformation reasons. Okay, section 9, cycling rate dependence. While we all desire to charge faster and discharge faster, right, transporting lithium ions faster to reduce wait time for a device to charge and discharge, the high rate capabilities of lithium ion batteries are really hindered by kinetic factors, such as slow diffusion of the lithium ions in the electrolyte and the electrode. And this can contribute to decreased capacity that you get in a device. So here you can see the plot from Yetming Chang's publication again, in which as you cycle faster and faster, so increasing C rates, as you can see here, you can see that the capacity drops. And so you can also see that there are some possible solutions in which if you nanostructure a material and make the particle size smaller to a certain extent, you can achieve higher surface area and thus shorter diffusion lengths between the surface of the particle and the center of the particle. So you can see here the capacity that can be achieved for a bulk type material versus a 6 nanometer particle. You can see that diffusion rate can be faster, but the capacity that that can be achieved is less than that of the bulk. So there's a balance between the capacities the high capacities that you would want to operate at versus the capacity at which you can achieve at those high rates. Section 10, mechanisms of failure. So I mentioned a few mechanisms of failure in a battery, overcharging, going outside of the optimal voltage window, and so on and so forth. But one of the important mechanisms of failure, if not controlled, could be the solid electrolyte interface formation. So that's the formation between the electrode and the electrolyte. So far, I haven't gone into great detail as to what the electrolyte actually is. In your lab module, you'll be using 1 molar LiPF6 in a combination of 2 carbonate-based solvents. We'll discuss in great detail in person, why that is an optimal and standard electrolyte. But for now, let's just talk about what can happen in terms of interactions between the electrolyte and the electrode, as well as the 2 electrodes. So you could see here that upon lithiation, what can happen is that there's uneven deposition of lithium, And as the lithium grows, it forms a dendritic lithium. And what you could see is that as it grows and grows, as this dendritic lithium grows and grows, that it can actually go from one electrode to the other electrode, and eventually will cause a cell, a short circuit. And of course, that is undesirable, and that could lead to some catastrophic effects, right? Now, the solid electrolyte interface isn't always, is not always a deleterious effect. In fact, some solid electrolyte interfaces that form will actually be beneficial. They can actually protect the surface. They can actually protect the electrode surface from forming other unwanted phases that could contribute to increased polarization or other adverse reactions. And so the moral of the story here is that you want a controlled solid electrolyte interface and not an uncontrolled solid electrolyte interface. However, this interface, the interphases at the interface, is actually quite dynamic and can change as a function of charge, as a function of the cycle. So it could change from the first cycle to the second cycle to the third cycle. So it's actually quite dynamic, and a lot of work has been done to study what actually forms, what chemical species form, what phases form at this interface. And so far, we made a lot of headway, but we still have a lot to learn in terms of what this dynamic interface actually consists of.